Muted.
All right, well, I think we're going to go ahead and get started now that it's a couple minutes after 1. So just like to welcome you to this webinar. My name is Nicholas DiOrio, and I'm an engineer on the System Advisor model team. And I've primarily been responsible for developing the battery model that we're going to walk through today. As you have questions during this presentation, please feel free to type them into the chat window, and I may not address them during the presentation, but I plan to leave ample time for questions. And I'd also like to point out that this presentation will be recorded, and the slides and the video will be available on the SAM website, which is sam.nrel.gov. And the video specifically will be posted at sam.nrel.gov/videos. So with that, let's go ahead and get started. So today we're going to be talking about the new behind-the-meter battery storage model in SAM. And here is what we're going to be looking at. So I'm going to give you an overview of the battery model, kind of what it is for, what kind of questions you might be able to answer with it. Going to walk through some of the financial inputs that you'll need to evaluate your system, as well as the technical performance, how you choose to dispatch your battery to maximize the economic benefit. And then I'd also like to point out some upcoming features of the battery model, which will address some topics that are of a lot of interest for behind-the-meter storage. I'm then going to walk through a demonstration of how to use the model, and then you'll all have opportunities to ask questions and anything that I might have missed. So what is the battery model in SAM? It's a techno-economic model for behind-the-meter residential, commercial, and third-party ownership systems. So it's worth pointing out that it's not looking at other topics of a lot of interest in storage, including frequency regulation, transmission distribution deferral, those kind of utility scale battery storage topics of interest. Those are not currently modeled in SAM. So we're just interested in behind the meter, which you would typically think of using for demand charge reduction or energy shifting based on time of use rates. So within the battery model, we have a couple of different types of batteries that you can model. You can look at lead-acid batteries or lithium-ion battery chemistries. With the analysis, you can look at a system lifetime analysis, which includes battery replacement costs. And this is an important consideration because unlike a lot of renewable energy installations, batteries depend quite heavily on how you cycle them. And so depending how you use the battery, you might need to replace it several times during, for instance, a 25 or 30-year period. And those replacements introduce large capital replacement costs that you need to consider to really evaluate the benefit. So the model is fairly detailed in the sense that we have models for terminal voltage, capacity, temperature, and then right now we currently have a manual dispatch controller, which I'll walk through in some detail. So the first thing that you have to do in order to use the battery model is to start a new project, and you have to select a detailed photovoltaic case, and then you have to choose between one of 3 financial options. And so this is where the battery model is in SAM. So it's either in the residential, commercial, or third-party ownership systems. And then on the sidebar here, you can see the battery storage tab highlighted. And so within that page, you have to click Enable Battery on the top, and that's going to get you the list of inputs that you need. So the kind of financial parameters that you might be interested in looking at for your battery for a system lifetime analysis is going to include things like your upfront and replacement costs. So you need to have a rough estimate of how much the battery is going to cost per kilowatt hour. And so there's various estimates out there for this right now and various targets, and so it's up to you to choose kind of what target you're looking at. You can specify how you want to replace your battery. So for instance, everyone has a cell phone or computer, and you notice as you use that device daily over the course of a couple years, you start to notice that the battery doesn't last as long. And so within SAM, you can choose when to replace that battery. So for instance, when the max capacity is at some percentage of the original maximum, you might want to replace that battery. Or you could also choose to replace it at a certain schedule. So for instance, if you want to replace your battery every 15 years, you could program that. And then you also can choose what replacement cost to use for those battery replacements. And you can also look at things like, what if battery costs decrease significantly in the future? So SAM can help answer those kind of questions. For the battery performance models, I've really only highlighted the very top part of the input page here. And this is really just to get started. And I'll be walking through some of the more detailed inputs during the demonstration. But to get started, as I mentioned, you first have to enable the battery model for your case. And then the bare minimum kind of inputs that you need to get started are to specify the desired battery bank size in kilowatt hours. And as you scale that size in kilowatt hours, you need to make sure to also scale the bank voltage. And this is so you have realistic amounts of current going through your system. So you can imagine if you scale your battery from 3 kilowatt hours to 1,000, you don't want the bank voltage to be 12 volts. So that's not a physically realistic system. And so you can also specify the number of cells. So if you have various information like a data sheet, and you know how many cells you have and you know their properties, you can specify how many cells you have in series and then how many strings of battery cells you have. And then the other input you see here is the battery type. So here you can select either lead acid or lithium ion types. And we have several different kinds of lead acid and lithium ion batteries listed. And essentially what this selection does is to populate defaults on the battery page. So there are two models. There's a lead acid model and a lithium ion model, and changing between types of batteries simply changes the defaults that you'll see on the page. So the manual dispatch controller that we have in SAM allows you to schedule based on the time of day and also the month, whether you want to charge from the grid, whether you want to allow to charge from excess PV, if you want to allow discharging of the battery, and then how much capacity of the battery do you want to discharge over that time period. And with this kind of controller, you can set up fairly detailed control strategies that will allow you to tailor the dispatch. And it's worth noting ideal for peak shaving applications and doing demand charge reduction. And the reason that is because typically demand charges are evaluated on a 15-minute basis. And so you can see here that this is an hourly dispatch controller. And so there's some limitations there. And then also, you might not know exactly when your peak demand is going to be. And so trying to set up the controller a priori is not necessarily going to be the best way to reduce your demand. Despite these limitations with this controller, it does allow you to start looking at how you would evaluate these kind of questions and starting to get into more advanced strategies, which I will talk about more. So within this controller, you can also specify things like the minimum state of charge of the battery and the maximum state of charge. This is important for your battery degradation. We also have a feature that allows you to choose the minimum time at a charge state. So this is particularly relevant for very short time step simulations. So the battery controller and the PV model can run down to 1-minute time steps if you have weather data and load data at those time steps. And so we basically this minimum time at charge state allows you to reduce rapid oscillations between charging and discharging. There's also a grid recharge mode, which, as you'll see in period 4 here, if you have the boxes checked charge from grid and allow discharging, once the battery is has discharged to its minimum state of charge, then grid charging will kick in automatically for that particular mode. And this controller, again, is relatively not complicated to set up, but it takes a little bit of effort. We're going to spend some time in the demonstration to look at that. So real quick, let's take a quick look at what this controller is doing. So in the top left graph, you can see a stacked chart that shows how much of each component, those components being your PV system, the grid, and the battery. So how much of each of those is going to meet the electric load during certain times. So the blue is the PV contribution. So that's during the middle part of the day when the solar resource is high. All of the load is going to be met by PV. In this particular scenario, the battery dispatch controller has been set to discharge during kind of the peak evening hours. And so you see that evening, or that orange spike in the middle of the largest peak. So the battery is going to meet some of the load. And then for the rest of the evening, you see the red contribution, and that's the grid taking back over and powering the load. In the bottom left plot, this illustrates, if I go back one slide, this far right column, the percent capacity to discharge. So this column allows you to specify over each time period how much of the battery energy do you want to allow to discharge to meet the load. And this controller was added basically so your battery doesn't just naively discharge to meet the full load during one time period. So it allows you to make your battery last kind of over an extended period of time. And so in the bottom left here, you see this kind of stair steps. And basically, every over 4-hour period, the battery is allowed to discharge up to 25% of its original capacity. And so in this first stair here, it didn't actually discharge a full 25% because there was still some PV available. But in subsequent hours, it discharges at the full 25%. So as I've mentioned a couple times, it's really important to consider how cycling the battery affects the battery lifetime, because as you cycle the battery loses capacity, and then you eventually have to consider replacing it. And that introduces potential large capital replacement costs. And so this plot on the bottom left here, this is the kind of information that you, the user, have to input. So we leave it up to you to input kind of the degradation of your battery. So depending on the average depth of discharge and the number of cycles, you choose kind of how fast it degrades. So this green line here would be if you cycle your battery to an average depth of discharge of 80%. So that means starting from a full battery, if you take it down to the point where it only has 20% charge remaining, that's a depth of discharge of 80%. So in this case, after about 1,000 cycles at this depth of discharge, the battery has degraded to 80% of its original maximum capacity. Whereas for the blue line here, if you only cycle it to an average depth of discharge of 20%, so you're not discharging it as deeply, you can get about 5,000 cycles before it has degraded 80%. In the top right here, you see a simulation where there have been a couple of times where the battery bank has been replaced, and so this introduces those large capital costs you see. And then finally, in the bottom right here, this is kind of just illustrating how the model applies that degradation curve. And so the blue line shows as the number of cycles increase, the orange line decreases, where the orange line is the battery capacity. So basically the maximum capacity of the battery. You see as the blue line reaches the top, then the battery gets replaced, and so basically a new battery gets installed. And so this kind of just illustrates how the model applies that degradation curve as you cycle the battery. So as I spent some time explaining on the dispatch slide, the current battery controller is somewhat limited in that it's not really ideal for performing peak shaving. And so we've been in the process of developing an automated dispatch controller to do peak shaving. And it uses a 24-hour look ahead to get the weather and the load forecast. And then within that 24-hour period, we look for the peak grid usage over that period, and then shave the peaks every day based on the battery capacity and the ability to recharge from the grid in that time period. And there's also another feature where we will allow you to specify the target power to shave to. Otherwise, the battery will just kind of naively assume that you want to shave your peaks as much as possible every 24-hour period. Now, I should note that this future controller is not an optimal dispatch controller. It does not consider things like the rate structure, so it assumes that any peak that you are shaving is equally valuable. And so yeah, it's not optimal, but it is going to be automated. And it's worth considering before you really do an optimal peak shaving whether or not you can actually come close to achieving that with a commercial controller. So, you know, does a commercial controller have a perfect forecast? Does it have the ability to really know like what the load is going to be? And so those are very important questions to ask, but we believe that this future feature will do a better job of addressing those questions. Another feature that we're going to add is the ability to tailor the amount of power to charge from the grid. And so this is basically just so you don't actually introduce new spikes in the load by charging your battery. So you can kind of tailor how much grid power to allow every time period. And so we're expecting to release the next version of SAM sometime in late 2015 or early 2016. And these features, plus many additional features that my colleagues have developed, will be available. So with this, I would like to do a demonstration of the battery model, and so we can actually see it in action. How do you actually set it up? How do you start deriving information from it? And so the question that I would like to ask is, what is the benefit of adding batteries to PV for a commercial building in Los Angeles? And so this is a pretty contrived question because one of the main benefits of behind-the-meter storage is peak shaving, but it really depends on the utility rate structure, and there really aren't necessarily many places in the United States where the rate structure makes quite as much sense as Los Angeles, and SCE's, some of SCE's rate structures appear to be very well set up to do peak shaving. And so with this demonstration, we're going to create a detailed case with a commercial financial model. We'll go ahead and input details about the location. We'll set up a PV system and a battery system, and then we'll work on tailoring the dispatch strategy to the electricity rate tariff structure. And then to kind of evaluate the benefit, we'll compare the battery installation case to a no battery case and look at some financial metrics to see what kind of information we can find. So with this, go ahead and create a new case. So I have the current released version of SAM. So this is version 2015.6.30. So you open up SAM, you'll see this page here. Click Start a New Project, and then right on top here we have the photovoltaic detailed model. So I'll click that, and then this brings up the list of all of our various financial models. So we're interested in a commercial system, so I'll click Commercial and click OK. So this brings up SAM here. On the left here we have various input pages that we'll need to populate with some information. And we won't actually have to go through all of them in detail, fortunately, but just to get started. So as I mentioned, we're interested in Los Angeles. So just to get started, we'll use the SAM library, which has a bunch of weather resource files. So we'll just select this Los Angeles TMY2 file. We'll go ahead and leave the module alone. So, and the same with the inverter. So if you wanted to, you could go through and select an inverter or input your own information about an inverter or PV module. So the system design page is where you're going to size the PV system. And by default, for the commercial case, the PV system is 200 kilowatts and has a DC to AC ratio of about 1.1. So you can see kind of those properties here. And we'll just go ahead and leave the rest of these properties alone. So if you wanted to, you could look at various types of fixed axis or one axis trackers. You could modify the tilt and azimuth and all that kind of more detailed information. You can look at shading and snow losses, which we're just going to ignore for right now. There are additional losses, soiling, kind of wiring losses you could get into a lot of detail with, which we're just going to leave as the defaults. And here we'll start to get into some of the more relevant pieces for our simulation. So as I mentioned, for batteries, we're primarily only interested in looking over the entire analysis period, because a one-year simulation is not going to capture the complexity of battery replacement costs. So on the lifetime page, I just changed this to be over the entire analysis period. Before we get into the battery storage page, let's just go ahead and take a look at the electric load. So SAM provides a kind of a default load profile. And this particular profile looks pretty standard, has low power usage in the morning, kind of ramping up as people get to work, kind of peaks in the middle of the day into the late afternoon, and then drops off in the evening. For this case, we have quite high peak loads here as default, so I'm just going to go ahead and cut those in a quarter. So now the peak load for the year is about 420 kilowatts. So let's go ahead and start looking at the battery page. So we're going to go ahead and enable the battery. And here you see some of the inputs that you saw on the slides. And so first thing we want to do is consider roughly how large of a battery system do we want. And so for this case, let's go ahead and just say 50 kilowatt hours. And I'll go ahead and scale the voltage. I'm not completely familiar with what the voltage of such a system would be. But if I type 1,000, I can see that the current is not, it's not like 60,000 amps or something. So it's something potentially reasonable. For the battery type, I'm going to go ahead and leave it as a lithium ion with a NMC anode-cathode combination. You'll see we have 6 different pairs, and again, these just populate defaults within the model. And you can also change any of these properties. So for instance, if I knew that the nominal voltage was 3.8, I could change that. So really, we just try to provide you default. So for those of you that might not have this kind of detailed information, you don't really have to mess with it. So here you could enter the cell capacity if you knew the cell capacity was different. This max C rate of charge and discharge basically tells SAM how fast you want to allow your battery to be discharged. So a C rate of 1 implies that you're going to allow your full battery capacity to be drained within 1 hour. If you wanted it to last 5 hours, then you can change this to 0.2, which is 1 divided by 5. For now, we can go ahead and leave it at 1. And of course, there's really two metrics when you're sizing a battery system. The first is kind of the kilowatt hour capacity, and then of course you're also interested in the power of the battery, so the kilowatts. So this current model of SAM doesn't actually report the kilowatts directly, and that's because It kind of depends on how fast you want to discharge your battery, but we can easily calculate it based on this discharge of 1 per hour. So we have roughly a 51 kilowatt hour battery. If we allow that to discharge in 1 hour, then that's a 51 kilowatt battery. And so you can kind of change those discharge rates around to get different power throughput. We have single point efficiencies in SAM, so we assume that the battery is connected on the AC bus such that you need to reinvert the power to charge the battery, and then subsequently when you discharge the battery, you need to invert the power to put back on the AC bus. And so very simple single point efficiencies. Then we get down to the dispatch controller. So I've already kind of gone through this in some detail, but I'll go ahead and wait here to actually tailor this until we look at the electricity rates. As I mentioned, the user is going to be responsible for inputting the lifetime information, so it's kind of up to you to either have some data sheet information or make some assumptions. So for instance, if you say, well, I think my battery is going to last a really long time, so I'm just going to multiply everything by 10, so I don't have to worry as much. But I would certainly encourage you, if you're doing a very detailed analysis, to try to get from the manufacturer some kind of cycling information, so you have more justification in your analysis about why you did or did not replace your battery. So down here we get to the battery bank replacement portion. And so I'm going to go ahead and say that we want to replace the battery at some specified capacity. And I'm going to go ahead and say once the battery can only charge to 50% of its original max, then let's go ahead and replace it. And let's be really optimistic and say that battery prices are $300 per kilowatt hour whenever we have to replace them. So there's additional inputs for thermal behavior, but for now we're not going to worry about those. So real quick, we'll take a look at the system's cost page. We'll leave everything alone except, again, I said we're going to assume that we're a very optimistic price of $300 per kilowatt hour. And just to give you some perspective on that, the Tesla Powerwall was recently announced there's a 7 kilowatt hour battery that's a daily cycle battery that was listed for $3,000. And so that would be about $430 per kilowatt hour. And that, of course, might not include things like installation or an inverter, depending on if you already have it. And so $300 is pretty low. We'll go ahead and leave other things like financial parameters alone, just to point out that you can do things like analyze the system cost by taking out a loan. You can look at inflation. You'll want to look at the real discount rate, because we're going to be looking over a 25-year period, and in that period, you know, the time value of money becomes important. Finally, you could look at incentives here. And so in California, there's actually some rather large incentives for advanced energy storage. To my knowledge, they're still available. I won't enter them right now, but I believe it's about $1.62 per watt. So if we have a 50 kilowatt battery, you can imagine that's quite an incentive. So that's potentially, you know, tens of thousands of dollars of incentive. That particular incentive only covers up to 60% of the installation cost. So let's see, we're saying at $300 per kilowatt, our battery is only going to cost, you know, $15,000. And so if we wanted to do 60% of that, we could enter an incentive of $9,000 here just to illustrate that that's a possibility. So this is one of the most important pages, in my opinion. So for behind the meter storage, you need to know the utility rate. So we're in Los Angeles. I just click this button, search for rates at the top. One of the most useful buttons in SAM. You just look up Southern California Edison. We have commercial rate structures. I happen to know that GS3 option B is a pretty interesting rate structure to look at for demand charge reduction. So I click download and apply. We go ahead and verify that it applied. So we have time of use energy rates. We have demand charges. They're fixed. We also have time of use demand charges. And so as we look at programming our dispatch controller, I'm going to focus on this peak period here where we have time of use demand charges. So this period 3, they're $18.54 a kilowatt on top of whatever the fixed demand charge is. So let's look at trying to reduce that. So between June and October, from 12 to 6 p.m. So if I go to the battery storage page, just make this all 1 to start with. So 1 is just allowing to charge from excess PV. So we pretty much always want to do that. Otherwise, we're going to have to dump the PV. So period 3 says let's charge from PV, but also allow discharging. So June to September from 12 to 6 p.m. Let's put 3. And right now it's set so it can discharge up to 25% of the capacity every hour. So we could see that that would only last 4 hours if we ended up using the full battery. So let's back it off just a little bit and say 20%. And that'll give us a little bit of a buffer. Let's say minimum state of charge 30%. We can go ahead and leave it as 95%. You could, of course, change that. And then let's just go ahead and click simulate and see what we get. So up here we can see some metrics. We have the battery efficiency, 92%. We have a payback period of 13 years, a net present value of the whole system of $68,000. So this tells us that if we were to make this investment in this rate structure with this system, that would be profitable. But let's take a deeper look and see whether or not it actually makes sense with the battery. So we have some outputs here, and I like to look at so if I recall, we're only discharging a few months of the year. And so you don't see actually any power coming from the battery most of the time. And this is because we have so much less PV than we have load that the battery never charges. So let's go ahead and in the middle of the night here, let's make a new profile and call it profile 2. And this allows the battery to charge from the grid. If I click resimulate, start to see some battery usage here. you can click and look at stacked area on left y-axis and see that indeed we do have a little bit of battery power being discharged over the period of 12 p.m. to 6 p.m. And so it's kind of up to you at this point to start looking at your load profile and tailoring it a bit further based on kind of the behavior you see. So for instance, you might look at your load profile and say, you know, on this particular day, I actually have kind of a peak earlier in the morning, so I might need to dispatch my battery in the morning. I might see that for a few days. And so you actually see kind of a large area up here that you might not even really be able to shave in an intelligent way with the size of battery that we have. You might not want to discharge from 12 to 1. You might want to save some more of your battery and use more of your battery over a few hour period. So I reduced the payback period here by a few months. And so, as I mentioned, it's not ideal for peak shaving because you have to really kind of dig into your load profile and then start tailoring the controller kind of very specifically depending on the month and the hour. But you can start to chip away at some of the demand charge. And perhaps one more interesting set of outputs that I'll have you look at before I wrap this up and jump to questions. So there's this electricity demand charge without system. And then electricity demand charge with system. And so you can see here that over this period of time that we put the battery controller on, we actually are reducing our demand charge by several $1,000s a month. And so you can imagine that as you spend more time actually really carefully tailoring that schedule, you can start to chip away at that demand charge. But the question is, the way that I have it scheduled right now, is the battery system worth installing? And so let's look at the net present value is $76,000. So let's see. If I turn off battery storage and just leave a PV system. So actually, it was more valuable with the battery system, and that's with very little work tailoring the dispatch strategy, as you saw. Now, of course, I'm assuming a very optimistic price for batteries, but that just illustrates how you start to look at some of these questions with SAM. There's also a battery macro that you can compare a PV system versus no system versus PV with battery, look at all of these charges, look at kind of some of the net present values. And so there's a lot of interest in battery storage. We're continuing to develop battery storage in SAM, and we hope to continue along more advanced strategies. And so with that, I will go ahead and wrap up my demonstration, and I would like to go ahead and answer some questions. So let's see. So I have a question. The payback analysis is for the entire system, PV and batteries, not just the battery payback. So yes, that is correct. And one interesting thing about using the payback period for evaluating batteries is it's kind of a complicated metric to use, especially as batteries become replaced. And so the payback period metric here is actually can be somewhat misleading. So this payback period is 12.7 years to the first time where you have actually made more money or saved more money on using your system than the system cost. But if you need to replace your battery later on in out years, it doesn't account for that. So for instance, if in year 14 you had to replace your battery, then your payback period is not really truly 12.7 years. So you're going to have to pay off that replacement cost. So I would encourage you to consider both the payback period as well as the net present value, which is going to take into account that whole 25-year period. Okay, so Nathan said I could ignore his question, but I'm going to answer it because the answer is hopefully yes. We do plan to include more default battery technologies like flow batteries. So some of that is pending the projects that we're approved to do through the Department of Energy, but there's also a lot of interest in flow batteries, and we're starting to look at how we could incorporate some of those models as well. Okay, I have a question from David that says, I haven't allowed any battery use except June through September, so it should improve if you allow discharge at select times, but all year. So yes, I mean, you could certainly allow it to discharge all year and start to tap into some more demand charge savings. And at that point, you really just have to consider things like whether or not it's worth it to cycle it every day based on your battery degradation. But yes, I would, if I were to tailor this controller more specifically, I would go through and probably tailor it to discharge each month, because there are still very significant demand charges all year. So I hope that kind of addresses your question, and if not, please feel free to follow up. Okay, so I have a question from Jeffrey. Would the model work to provide battery information for a site with no PV assets installed? So that's a great question, and there is a lot of interest in just evaluating a battery. So yes, if I go ahead and go to my system design page, you can see we have 200 kilowatts of PV installed, but we kind of have a cheat for this. So if we go to the losses page, and then there's this curtailment and availability, if I click edit losses and then enter 100%, so basically we're going to curtail the entire PV output. Then on the systems cost page, just zero out the PV module costs. And you could you need to decide how you're going to incorporate inverter costs into your system. So maybe your batteries have micro inverters or something. So you might actually need to buy inverters. But for now, you could zero those out as well and just look at the battery cost. And so you can start to look at battery only. So this kind of gets, so you can see we're not really shaving much of the peak with just the battery, but the battery is really small compared to the load. So that's one reason. And another reason is I didn't really spend a lot of time intelligently setting up the controller. So we're probably missing a lot of peaks And but yes, that's a great question. Okay, so there's a question that I'm not sure if I understand. What about residential post NEM 2.0 if full credit is not given from SDG&E? So I'm not quite sure what you're asking there, Dustin. So if you want, feel free to follow up with me, and I can try to get you an answer. Okay, so there's a question, what if you want the grid as a backup only, so that you really want 100% solar and battery, but not a true off-grid system? So basically, in that scenario, I think you're saying that you would want to be able to turn the grid on in certain scenarios, but not use it to meet the load. So I think in that case, you really just have to size your PV system and battery appropriately given your electric load. So kind of the way SAM is set up is if you don't meet your electric load with PV or batteries, then it's going to assume that you have to buy that power from the grid. So I think you could probably do the analysis that you're looking to do. I'm not quite sure if I'm understanding what you want, but in SAM is a grid connected model from the perspective that we always assume that if there's not enough renewable energy resource, then you're not going to then you're going to use the grid. So I hope that answers your question. So comment from David, I assume you mean peaks are equally valued per kilowatt shaved. Yes, that's correct. So it's a fairly naive automatic dispatch controller that will initially be released, and it basically, as David says, it doesn't assume anything about the peaks. It just assumes that you want them as low as possible over each 24-hour period. And so the time of use rate, it doesn't care about that. It just says, I want to, given the battery capacity that I have, I want to shave my peak as much as possible. And perhaps later on, we're going to actually be looking at more dispatch control strategies that will start to incorporate some of that information. So we really just kind of wanted to try to get an automated controller out there since there's a lot of interest, and then start kind of refining it from there. And so there's a question, is the capacity to discharge the depth of discharge or the amount removed from the battery? So I assume we're talking about this column over here. So basically what this column does is it's talking about at the beginning of the discharge period. So for instance, at 2 p.m. here, assuming the battery is fully charged, we're talking about 25% of the energy that's available between kind of this usable portion of the battery. So between 30% and 95%, we have a certain amount of kilowatt hours, and then we're allowing 25% of that original amount to be discharged every hour. So I hope that answers your question. So I'll go down and look at some of the newer questions that have come in here. So there's been a lot. So I'm sorry, I've been looking at older questions. So there's a question, when we are designing ESS, which is basically storage, we specify the inverter and capacity. So for example, 30 kilowatts and 60 kilowatt hours. Is there any way to set the maximum discharge of 30 kilowatts for a 60 kilowatt hour battery? So yes, you're correct. The way to do that is through the C rate. So if we do a 60 kilowatt hour battery and we want basically a 30 kilowatts, so that's going to be 2-hour battery, which is 0.5 C rate. So basically that's going to allow you to discharge your full capacity in 2 hours. And so that limits it to 30 kilowatts. So there's a question from Nathan. Are there plans to have a manufacturer battery database, much like Sam has for inverters and modules? So there's been talk of that, and it is possible. Right now we just have this kind of default chemistry type. The main issue with creating a battery database is it's kind of hard to classify all batteries within a certain amount of inputs. So I mean, obviously we've done it for the battery page here, and then maintaining that database becomes kind of an issue, but there is interest in it, and I would say we are interested in doing that if we have time. So, but at this time, there's no work being done on that. So another question, is this model specific to peak load shaving? Has it been used to simulate off-grid systems where diesel generators are the competing cost? So no, it's not really been used for off-grid systems. So it's primarily a grid-tied model, and you could do an analysis comparing diesel generator costs, but you'd have to use some kind of existing cost basis, so you can't actually do the diesel generator analysis within SAM. And I know we're running short on time here, but I think there's just a couple more questions I could address, so people can feel free to jump off if they need to. So there's a question, as you have it set up, does the battery controller discharge on summer weekends? So that's a great question. Yes. Right now the manual dispatch controller does not distinguish between weekdays and weekends, and that is of course something that we would like to improve upon. So weekends are available in the electricity rates page controllers, but not within the manual dispatch controller. So that is something that I will hopefully be adding in the next couple months. Last one, okay. So I'll answer this one more question. So on the electric load, how do we show monthly values that meet our client's actual load? So I want to edit the kilowatts, not just the kilowatt hours. Okay, so how do we show monthly values? Okay. So I'm going to let my colleague Janine Freeman address this question just because.
Sure. On the electric load page, we have 2 ways to input and edit your load data. So this first one that's selected here, the input time series load data, if you hit the edit data button, that would be, this is where you can edit to represent actual load data, and you can specify it either hourly or sub-hourly. And that is where you would be able to edit it to make it closer match actual client data. And then if we switch over to the other input option, we'll cancel this one. And then at the top of the page, the blue box, oh, we're in commercial, so it won't show up. In a residential model, there's another option for a building electric load profile estimator, which Nick is navigating to at the moment. And that option asks, instead of for hourly data, it will ask you for characteristics about the building that you're modeling. It's currently only available in the residential model because the assumptions that are underlying this model are very specific to residential buildings rather than commercial buildings. But for a residential system, you can specify some of the characteristics of the building that you're modeling, and then the monthly load data option at the bottom will scale the profiles that have been created to a customer's monthly actual bill. So customers are more likely to maybe have their monthly consumption than hourly. And this will just scale an estimated profile to that monthly consumption number. So those are the two more detailed ways to edit the electric load that the battery will then be looking at in, the battery and the PV will be looking at in the simulation.
Great. Thanks, Janine. With that, I think we're kind of have run a bit over, but I want to go ahead and take this moment to plug another opportunity that you could have to ask questions about SAM, either the battery model or any part of SAM. So we have bi-weekly SAM roundtables now, and so these occur on Wednesday afternoons at 2:30 to 3 p.m. Mountain Standard Time. And I don't know if, I think these might be advertised on the SAM homepage. So I would encourage those of you that have lingering questions to please go ahead and register and join us for this time period. So it's free. And with that, I'll go ahead and wrap up. And I thank you all for your participation. And please look for this video on sam.nrel.gov or ask any questions. And thank you again.